Hi all, welcome. I'm delighted to present to you today Professor Minghui Cheng, who is Assistant Professor in Civil and Architectural Engineering / the School of Architecture at the University of Miami. Previously, he was a postdoctoral associate at Systems Engineering, Cornell University. He obtained his PhD in structural engineering from Lehigh in 2021, and before that, his BE in civil engineering at Hunan University in China in 2016. His research focuses on the system digital twin of infrastructure systems and sustainability-informed lifecycle management. He does this with an emphasis on surrogate modeling, optimization, and machine learning. The title of his talk is going to be, I'm going to struggle with this, but I'll try. Meta-learning-based surrogate modeling and system digital twin for lifecycle management of infrastructure systems. Thank you very much, Professor Cheng, for doing this, and the floor is all yours.
Hello, can everyone hear me?
Yes.
Okay, great. I'm very happy to be here today. This is the first time that I use the Miami green color to do this presentation. The color looks great on the slides. Thank you, Professor Suranani, for the kind introduction, and thank you for giving me this opportunity to do this seminar. This is a great opportunity for me to talk about my research and to reach out to the PhD students in the department. Today, my presentation title is Meta-learning-based surrogate modeling and system digital twin for lifecycle management of infrastructure systems. This is the outline of my presentation today. First, I will briefly introduce lifecycle management and the motivation of my research. Then I'm going to talk about my three major research thrusts. This will include the lifecycle management with preferences, meta-learning-based surrogate modeling, and system digital twin. And finally, will be the conclusions and future work. Now let's get started. First, the introduction. The civil infrastructure systems are very important to our society. And unfortunately, they are subjected to natural hazards and lots of deterioration. And as we all know we have all experienced, we know that the climate change is happening right now. And unfortunately, climate change can accelerate the deterioration of structures. And also with climate change, we will see higher magnitudes of natural hazards and higher frequencies of natural hazards as well. So this will lead to an increasing loss of our infrastructure systems due to the climate change. So one of the ways to battle climate change is through lifecycle management. I always say that lifecycle management is like going to the hospital to manage your health. So on the left, this picture shows like bridge inspection. This is like you going to the hospital to do an annual physical exam. And if you find something bad, then you may need to do some repair. So this picture shows the bridge repair. This is like us going to the hospital to do a surgery. So the objective of lifecycle management is to minimize the lifecycle cost. So here is the general procedure of lifecycle management. We have to do the deterioration modeling on the structures. And then with the deterioration modeling, we will then assess the performance of the structure. And then we can evaluate the failure probability of the structures. And also important is the consequence evaluation of structural failure. So you can think of the failure consequence as divided as direct consequence and indirect consequence. Direct consequence usually involves you pay some money to rebuild the structure, but more importantly is the indirect cost. So the indirect cost on this left picture is it's a picture that I took before. It's a bridge closure that lead to a detour. And on the right, this is a picture showing a bridge collapse in Miami, which lead to casualties. Research have shown that the indirect cost is much higher than the direct cost. It could be like 10 to 20 times of direct cost. So we have to pay more attention to the failure consequence on the society and the community, which is the indirect cost. And with all this calculation, we are going to do lifecycle management. We have to know our strategy. So which options you are available. And with the LCM strategy, then finally we will do the optimization. Lifecycle optimization is computationally expensive. This is due to we have to evaluate structural systems. Like on the top left, this picture, this is a structural systems with 5 girders, and we always need to do because it's life cycle, we always need to do a reliability analysis on the time scale. It can be time-dependent reliability analysis. It could also be time variant reliability analysis. This means you are going to perform a structural reliability analysis at each time point. So this is computationally expensive. And what makes things worse is that when we are doing structural reliability analysis at each time point, sometimes we have to invoke very functions and commercial softwares that takes time. For example, on the left, this is a finite element analysis, which takes time. And when we are doing failure consequence evaluation, this is a traffic assignment to evaluate the detour times due to a bridge closure. So all these things are computationally expensive. So combined together, it is, I could say, lifecycle optimization is computationally expensive. And unfortunately, we have limited computational resource. So when we are performing lifecycle optimization, we are more like Dr. Strange before Thanos come. So Dr. Strange has the time to run 14 million simulations of the future. But if you watch the movie, you will know that the best solution is not good enough. So perhaps if Dr. Strange can improve his computational efficiency, then he may find a better solution. So that's basically what my research focused on. I focus on accelerate the computation lifecycle optimization. So here is a graphical summary of my previous and existing research and my current research. So my research focuses on improving the sustainability and resilience, and this is done by LCM, lifecycle management. And during my research, I also try to incorporate preferences of civil engineering stakeholders into the LCM. But at this point, this research only focuses on LCM of single structures and assets. But but I try to go bigger because we need to, as I said before, we need to focus on the indirect to better evaluate the indirect cost of the indirect failure consequence. So we need to go bigger. So my research tries to do system analysis. So that's why I propose something called meta-learning based surrogate modeling. And I want to go even bigger to complex systems. And we are now in a big data era. I also want to incorporate the power of big data. So I expand my research to system digital twin. And with the further development of system digital twin and the meta-learning based surrogate modeling, they can feed back to the decision making to help us better perform lifecycle management. So that's a summary of my previous and current research. And now let's get to the first part of my research, which is the lifecycle management with preferences, LCM with preferences. So the objective of this research thrust is that I want to incorporate preferences of civil engineering stakeholders into cost-effective LCM strategies. And I will first show you how I measure the preferences, and then I show you how I develop a cost-effective LCM strategy that can cater to the preferences of civil engineering stakeholders. So let's get started. First part, measure preferences. Decision makers are not likely to conduct timely maintenance if the benefit is in the distant future, for example, 30 or 50 years. And if the failure probability of structures is relatively low, you can think of like fighting climate change, or evaluate, you can think of purchasing auto insurance, whether you want to put large spend large insurance premium for your car. So this is something when the failure probability is relatively low. And so these attitudes are called time preference and risk perception. Decision-making models have been proposed, but they cannot be directly applied in civil engineering, because in civil engineering, we always encounter low probability, high consequence events, and long time horizon. So I did the survey. This is the first experimental work in the field. I conducted a survey involving low probability and long time horizon to calibrate the existing decision-making models. This is a typical question on the survey, given that you can see what money you want to, you can try to answer this question in your mind. So given that no intervention on a structure, given that no intervention on a structure will lead to a probability P1 of losing $500,000 at year T, how much are you willing to invest now to reduce the probability P1 to a smaller probability P2? So this is a typical question on the questionnaire. So there are 12 questions in this format. It involves 3 time horizons and 4 pairs of failure probability P1 and P2. So I calibrate something called delay and probability discounting models. Due to the time constraint, I won't go through the mathematical details on how to calibrate and select the models. But here is a histogram of all the survey response. So I want us to pay attention to this specific one. So for this survey, each row represents a time horizon and each column represents a pair of failure probability. So I want us to pay attention to this one. This corresponds to the question with the time horizon 50 years and the failure probability pairs of 0.001 to 0.0001, which is the smallest failure probability. So as you can see here, this blue rectangle shows that that's 0. This means that, as you can see, more than 50% of people won't invest any money if the time horizon is 50 years and when the failure probability is quite small. So this is something that we have to notice. Like for example, fighting climate change, the climate change effects will not become very severe until a very long time. So if my survey using my survey results, this will indicate that people will normally don't do anything, don't do repair or retrofits for climate change. So we have to think of some ways to try to incentivize people to do timely maintenance. And that's why I want to do this survey. So survey results clearly show the risk averseness and time preference of decision makers, and this is not good for climate change adaptation. So we have to try to do something to incentivize stakeholders to do timely maintenance. Now let's get to the second part of this research trust, cater to preferences. I specifically developed this LCM strategy for low rating planning. What low rating planning is that we will use low rating as a performance indicator for decision making on repairs. The current practice is that it's FDOT. It's interesting. When I did this research, I cited FDOT, and now I moved to Florida. So the current practice is that we will use periodic inspection, and the replacement threshold of low rating is 1.0, and this current practice is not cost effective. So I would like to develop a more cost-effective LCM strategy. This strategy is that the next low rating time is adaptive to current low rating results. And I also want to, as I said before, I also want to incorporate preferences of decision makers. And because this strategy is kind of complex because it's adaptive, we can't use some some heuristic algorithms like genetic algorithms, because this is a complicated adaptive strategy. So I use deep reinforcement learning to obtain the optimal plans. Due to the time constraint, I can't show the deep reinforcement learning, how I use deep reinforcement learning to solve the optimization, but I want to illustrate this LCM strategy. So here is a realization of a satisfactory structural performance. And as you can see, when the structural performance is good, this strategy will only conduct 4 low ratings. And when we have some worse structural performance, this is another realization. We will perform 5 low ratings. And even when the performance goes down to a threshold, then we will do replacement. So here is some interesting fact for this type of strategy. I consider 4 types of stakeholders. They are risk neutral, risk averse, more risk averse, and hyperbolic time preference, which is something I observed in my previous survey. So let's see the life cycle cost here. As you can see that the total life cycle cost for the 4 different stakeholders, they are very, very close. This is something traditional lifecycle management strategy cannot achieve. They would either have they can easily go up when the lifecycle cost can jump a lot when the person becomes risk averse. And this one strategy, you can see that all the lifecycle costs are very close. And if we look at the cost breakdowns, you can see that we are just distribute between inspection costs, repair costs, and failure risk. And this is very good. So I developed overall this cost-effective low ratings policies can cater to preferences of decision makers. So here is a summary of this research for us. I measured the preferences of civil engineering stakeholders through surveys, and I developed a cost-effective adaptive maintenance strategy that caters to the preferences of decision makers. However, at this point, my LCM is more on single structure and asset. I want to go bigger to be able to do system level analysis. And now so that's why I developed meta-learning based surrogate modeling. And this is the second research thrust. The objective of this MLSM, which stands for meta-learning based surrogate modeling, is that I want to accelerate system level lifecycle optimization through knowledge transfer. So overall, I will first introduce what is the framework, and then I will show you some applications. So the idea of meta-learning based surrogate modeling comes from this. So this is when I did the research with my former colleague. It's an LCM. When I did the optimization, I did the sensitivity analysis. I vary different cost metrics, so like different inspection costs, different failure risk, different maintenance costs. And as you can see, these 6 figures here, they have different magnitudes. However, we can clearly see that when we do the lifecycle optimization, you can see they have the similar shape. So that means perhaps we can, after we perform one lifecycle management optimization, perhaps we can use this knowledge to transfer to other lifecycle management. So that's why I try to do knowledge transfer. So traditionally, surrogate modeling is carried out from scratch when a new task arises. This neglects the prior knowledge gained from previous tasks similar to the new one. So on the left, this is the traditional way to perform lifecycle optimization using surrogate modeling. We have the true model. We run simulations to get data points, and then we will fit a surrogate model and then use this surrogate model to do the optimization. But this neglects the prior knowledge. So what I propose is meta-learning based. So we have the true model, we run data points, but right now we will try to use the lifecycle optimization task, the previous task. So that's here, prior knowledge. I will summarize the prior knowledge using a meta model and then combine the meta model with the data points to create a surrogate model. So I tried with this meta model, I can minimize the number of data points here to create an accurate surrogate model. So during my research, I found that the most important thing about this major research for us is not the algorithm. There are so many meta-learning algorithms, but the important thing is not the algorithm. It is how we define the similar task. So here is the definition of similar tasks in my paper. In general, tasks are similar when they share the same set of inputs and outputs and differ in values on a limited number of parameters. So here, let me give you an example. to understand this definition. So on the left, it's task 1. It's a 3-story building. I'm doing the seismic reliability analysis. And I found that if I use C30 concrete, please note that C30 is the concrete strength is a random variable. I found that the failure probability is not acceptable. So here comes the second task, task 2. It is the same 3-story building, but right now, because I want to increase the concrete strength. Is the failure probability acceptable right now? We will do the seismic reliability analysis. And now let's look at the definition of similar task. The same set of inputs and outputs. Yes, the input is the seismic, is the earthquake. The output is the like the failure probability because it's like the same story building, same type of analysis. So this match. And differ in values on a limited number of parameters. The parameter is the concrete strength. So based on my definition, these two tasks are similar. After they've defined similar tasks, so this is just the framework of this MRSM, some math, but I will skip that. If you're interested, you can go to read the paper. Here, I want to show you some example to help you to better illustrate this framework. So here is example 1, which is the McCormick function, f x1, x2. Please note that the a1, a2, and a3, they are parameters. The x1 and x2 is the input, and the f, which is the function, is the output. So here is the contour plots of the meta model I learned using meta learning. And here is the task 1. Task 1 is the original McCormick function on the left. That's the true function, the contour plot of the true function. And with only 10 data points here, I can see that MRSM already learned the general shapes of the function. With 20 points, the accuracy increases. And let's compare to traditional surrogate modeling, TSM here. With 10 data points, it's pretty bad. And with 20 points, it learns the shape, but it's not very refined. So compare the MRSM and traditional surrogate modeling. The better performance of MRSM comes from because the meta model, the contour plot of the meta model already capture lots of characteristics of this family of function, like all those tasks. Let me show you another example. This is a reliability analysis of nonlinear oscillator. So I show you the definition of the similar task in seismic reliability analysis. So this is the same thing. So I don't need to explain. So here I vary the mean value of some random variables of this reliability, dynamic reliability analysis. And what I want to point out is that I select 6 tasks and their failure probability has a huge range. It ranges from 0.002 to 0.05. In like seismic reliability analysis, you can tell that this is a huge range, which represent a large number of like in practice you can think of it as a large number of different types of buildings. Here is the result. So I compare the minimum number of data points required for surrogate modeling to achieve a target level of accuracy for the failure probability. And as you can see here, MRSM outperformed the TSM, the traditional surrogate modeling, a lot. And as I said before, all these 6 tasks, they had a huge range of failure probability. So this not only shows that MRSM is computationally efficient, it is also very flexible. So now let's look at some applications of MRSM. So this is climate change adaptation of bridge networks. When we are considering climate change adaptation, we will run into a large number of scenarios due to the deep uncertainties associated with climate change and socio-economic growth. So because there are a large number of scenarios, I think that, well, some previous scenarios, all these scenarios are similar. So when I give this definition, after I give this definition, then I can use the knowledge transfer. So this is the knob on the left shows the novel scheme. So this previous analysis, scenario analysis, I will summarize the meta model, and for each new scenario, I will use knowledge transfer. So basically, the computational efficiency is great on average. each new scenario analysis, I can reduce 42% of simulations needed. And now let's look at another application. I will show you more on this application because I like this a lot. So this is application that's called engineering fleet management. So it's the same thing, the same concept. So you can think of a fleet of ships. All these ships are of the same type. So we conduct maintenance on here a couple of ships, and then we can learn the knowledge and have a meta-learn policy. And for each other ships in the fleet, I can do the knowledge transfer. And for this research, I combine the meta-learning with the adaptive maintenance policy, the reinforcement learning to do that. So I use the algorithm called meta reinforcement learning. And for this application, I also compare another knowledge transfer paradigm, which is the pre-train and retrain, with the thing that we did, the meta-learning. So here is some case study 1. This is one fatigue detail, and there are 20 tasks here. Here is the comparison between the for all these 20 tasks. Oh, sorry, I forgot to mention. For the pre-train, I will use pre-train and retrain. That's a transfer learning algorithm. I will use the task 1 to do the training and then transfer to tasks 2 to 19. So as you can see here, the kappa m means the reduction of meta learning. Yes, let's look at some figures that's better to explain. So on this top 2, we have to first make sure our algorithm works. So I compare the meta learning, the meta learning and the traditional way of doing it, which is starting from scratch. So as you can see here, the meta learn policy at the very beginning, it almost reached a very good lifecycle management policy. So and if we compare the meta learned way and traditional way, you can see a huge improvement in computational efficiency. It can reduce 2 orders of magnitude, which is very good. And now let's look at the comparison between the meta-learn way, the red lines, and the black lines. Black line is the pre-train and retrain, which is the transfer learning. And as you can see that, the meta-learning policy outperforms the pre-train and retrain. But some important things shows in the second case study, which is the 2 out of 5 system. So it's 2 out of 5 system for fatigue details, and I compare 15 tasks here, and this is the table for the comparison results, but the figures better show it. So for this, because this is a system instead of one fatigue detail, one component, this means that we found that for the system, the similarity between the tasks become large compared to one component. So when the similarity of tasks become less, when the tasks become less similar, what will happen to the meta-learning policy and the pre-train? And as you can see that here, we first validate that the meta-learning algorithm, and compared to traditional way of doing meta-learning policy, still outperforms. And now let's look at the comparison between the meta-learn policy and the pre-train here. It is astonishing to find that the pre-train way of doing it, which is the transfer learning algorithm, doesn't work for this here. It can never even reach a near optimal solution. So when the similarity of tasks between tasks goes down, the transfer learning doesn't work anymore. And if you can see here on the previous slide table, there are lots of minus. What the minus means is that it is worse than just going from scratch, starting from scratch. But our meta-learn policy is much more stable. It increased computational efficiency a lot, and it remains stable. So the meta-learning algorithm is good. So let's summarize this MISM. I proposed the first framework to realize knowledge transfer for surrogate modeling, and then I applied it to climate change adaptation of bridge networks and engineering fleet management, and it shows astonishing computational efficiency. And the next step is here. The MISM, as you may notice, I can only transfer knowledge between similar tasks. So right now, if we go bigger and try to connect different types of systems, this is a totally different story. So the next step of my research is to try to go beyond, go to complex systems and try to incorporate big data into lifecycle management. And so this is something I did. The system digital twin. Oh, it's ongoing. And first, digital twin is a hot topic right now, but so here I want to first introduce the concept of digital twin. So for those, you may know the building information modeling. Here you have lots of drawings. And now, if you know structural health monitoring, now people are putting lots of sensors in our structures, in our buildings. And when we combine the sensor data and the building information modeling, this is something I would term it data fusion, then creates the digital twin. For this type of digital twin, because building information modeling is more for visualization, so overall, although you combine structural health monitoring data, this type of digital twin is still more for the visualization. Here comes another type of digital twin. You see here, this is a digital model, which is a finite element analysis. Again, we are now equipped with lots of sensors in our structures, and we want to incorporate those data. However, we try to combine the data with the digital model, but this is easier said than done. But I have data fusion. And for structural type of digital twin, we also need to put it on a time scale. So this is another type of digital twin here. This is done by a group in UT Austin. So this structural digital type, this type of digital twin is very good for predictive maintenance. And my research is more like this type, to do probabilistic analysis and maintenance. So the difference between my digital twin and the previous digital twin is that I focus on complex systems. So the challenges to digitalize complex systems has the two. First, the system is evolving. For example, if you have a new building, or we move a damaged bridge, this system totally changes. Like this is not like a plane or a car. Like you still have the kind of similar shape, but if you add a new building or remove a damaged bridge, the system looks totally different. Second, for complex systems, there are complex statistical correlations and dependencies that need to be considered. So I use the Bayes network for SDT. The reason why I choose Bayes network is the graphical nature can very well capture the evolution of the system. And as I said before, the digital twin, we have to do the data fusion, like incorporate the data. So the Bayes network can update variables of interest when data is available. Here is a general, it's just a simple example of Bayes network. If you are interested in, you can go to some textbooks or search online. Then I propose this performance-oriented SDT. So here is the graph showing this framework. First, I will store a knowledge graph. And then this performance-oriented SDT is a user-centric method. I can, given some user inputs, there are 3 steps to create a custom SDT. This slide, I will now introduce the design philosophy behind this performance-oriented SDT. There are 2 design philosophies. First one is set the boundary. Second is detach SDTs. So I first talk about set the boundary. Here, as you can see here, 2 figures comparison. The reason why we want to set the boundary is that when we perform system analysis, can connect for complex system, that's where you can consider it very large. You can even go to some asking, who am I? Why I'm here? What's the purpose of life? But as an engineer, we don't want to be philosopher when we are evaluating some complex system. So we want to set the boundary. So in essence, these 2 figures show you what set the boundary like. This figure, this orange node is a source node, which is the performance objective, and the blue nodes are data. So what this shows is if you have two data, what will be the boundary of this, the analysis of the system. But if you have another data source, right now, based on Bayes network, we can reduce the boundary of our analysis. And reducing the boundary of our analysis can significantly increase the computational efficiency. The second design philosophy is detached SDTs. Here I construct a same BM for two purposes. So as you here is a picture showing a bridge and has a measurement of the river depth. So we are using the river data D here to update the bridge risk R. For early flood warning, it is the same thing. We use river data to update bridge risk. And for long-term management, it is also the same thing. We will use the river data to update the bridge risk. But these two things, these two management problems is totally different, because for early flood warning, we will use short-term data like a peak, like perhaps in an hour. But for long-term management, like climate change, we need to do an average of like a 1 month or a year or even 5 years. So because we are processing the data in a different way, although these two management problems have the same BM, we have to detach this. So that's what I call detached SDTs. I did lots of programming, and I'll skip all those programming and mathematical details and show you like the result, an illustrative result. Here is a graph that it's a graph that I imagined. Like there are 36 nodes, and P1 is the performance objective. And if suppose that I have two data sources, X5 and X11, what will be the custom SDT looks like? So there are 3 cuts. First, the green are selected. So this is the first cut, and the second cut, and the third cut. And finally, we will get the custom trunk with some post-processing, we will get the custom trunk. And for accuracy, for the purpose of accuracy, we need to grow the trunk back a little bit and construct the BM through some parameter learning. And finally, I will transform this BM into an SDT because we have to make it on a time scale for lifecycle management. So let's recall that before it was a 36 nodes graph, which is very big. But right now we only have like 1, 2, 3, 4, 5, 6 nodes for our SDT. And with this is a huge reduction. And with this small size of system digital twin, we will be able to perform large system level analysis. And then I applied it. For this work, I actually coded how I transformed the BM to SDT. This is for bridge networks. The data sources that I consider involve the traffic flow from the traffic monitoring program, truck weight, and bridge monitoring. So this is I coded this SDT. This is the graph graph for the BM. And so summary of this research is here. I propose and implement the performance-oriented SDT for modeling and management of infrastructure systems, and it's an exciting and ongoing work. So now let's get to the conclusions and future work. For my previous and current research, like the first part, I measured the attitudes and perceptions of civil engineering stakeholders through surveys. And then I developed a cost-effective adaptive maintenance strategy that caters to the preferences of decision makers. And for the system level analysis, I proposed the first framework to realize knowledge transfer for surrogate modeling, and I applied it to climate change adaptation of bridge networks and engineering fleet management. And I also want to incorporate big data, so I propose and implement the performance-oriented SDT framework. So now let's get to the more exciting part, which is the limitation of my research and how I can improve, which is the future work. So for the knowledge transfer part, I can always observe negative transfer. So future work is needed to study when negative transfer will occur. This could be very difficult, but I want to try. And from my mind, I would like to explore. I show you 2 applications, but I want to spend more time to explore more situations that are suitable for knowledge transfer. And for each situation, like find a proper definition of similar tasks to define the boundaries of successful knowledge transfer. And for the system digital twin, like what I show you is how I cut down the graph to perform system level analysis. But for the performance-oriented SDT to work, I need to first generate a large-scale knowledge graph. And this is something that I'm currently doing, to generate a very, very large-scale graph that can go across multiple systems and going large spatial dimensions. And for the second future work I'm interested in is to develop a spatial and efficient spatial and temporal SDT to perform simulations of our cities and infrastructure system. And this is also something I'm very interested in. And finally, the acknowledgements I'm fortunate to get some research support during my PhD and my postdoc. And that's all for my presentation today. And thank you for listening. I will be glad to take questions.